So good afternoon, everyone, and welcome. So it is my great pleasure to introduce Sai Vinjanampathy. Sai obtained his PhD in 2010 from Louisiana State University, and then post his PhD, he was a research fellow first at the University of Massachusetts, UMass, and then at the Center for Quantum Technologies at the National University of Singapore. So this was between the period of 2010 to 2016. And then post 2016, he has held the assistant professor position at the prestigious Indian Institute of Technology, Bombay, and simultaneously a senior research fellow position at CQT in Singapore. So Sai mainly works on areas connecting quantum thermodynamics and quantum information theory. And I think he has a really wonderful review with Janet Anders back from 2016 on quantum thermodynamics. And if I remember this correctly, this was in contemporary physics. And today, Sai will tell us a little bit more about his recent studies on connections between quantum synchronization and quantum thermodynamics. So with this, let us all please welcome our speaker, Sai. So Sai, the stage is yours.
Thank you very much, Joseph. Thank you very much for the kind words. And thank you for the invitation. I'm very, very excited to talk to you folks today. So today, what I'm presenting in front of you is a discussion that basically involves several different fields. And my understanding from talking to Joseph offline was that we have a mixed audience who are doing classical physics, quantum physics, so on and so forth. So what I will do is introduce everything that I need and then present the results briefly. But I believe that there is a discussion session afterwards, so I'm happy to kind of go into any of the details during the talk or after the talk, so you feel free to interrupt me. So this, this picture in front of you is the lake that is attached to IIT Bombay. It's quite a scenic campus. We are the only green zone in the middle of quite a depressing COVID situation here in Bombay. So you know, once all of this dies down, I definitely invite you to visit us. I think these kinds of discussions and collaborations are more important than ever. So with that, let me just share with you the references if you want to look some of this stuff up. So the journey, you know, that I have been on relating quantum synchronization with various other fields basically is listed in two papers here. And I'm mostly going to talk about the second paper. So the first is a PRL from 2018, and the other is a PRE Rapid from last year. And this work that I'm going to present to you is work that I did with Naufel, who's an institute postdoc with us, a wonderful institute postdoc with us. Mikhail, who's my long-term collaborator, who's now in Japan. Vlatko, who's both at Oxford and CQT, and Saro, who's right now in ICTP. And Kwek, of course, who's a PI at CQT. And so with that, let me just take it away. The outline of the talk basically is as follows. So as I said, I just wanted to make sure that everyone's on the same page. So I will introduce quantum synchronization to you by first introducing classical synchronization. And once we've done that, I'll move over to quantum synchronization. And I'll use a lot of kind of analogies and intuition to kind of move us into the quantum regime. And then I'll present an example which is not going to be the main discussion, which is the van der Pol oscillator. It's the classic example in the field, and so I'll just talk about it so that we can draw some intuition from it. And then we'll move this over to the finite dimensional example, which is where all the work is. And once we've done that, we basically, I'll present to you the results about understanding engines via quantum synchronization, and then I'll conclude my talk. So once again, please interrupt me if you have any questions while we're having this discussion. So here is a classic picture from Wojciech Zurek's famous paper about the boundary between classical and quantum. And a lot of the quantum synchronization study, part of the reason that, that it's exciting is also because it actually is a phenomenon that is already available in classical mechanics. And so classical synchronization is, in fact, something that many of you are experts in, and is something that we've known in nonlinear dynamics for many, many decades now. And what that means is that when we move it over to the quantum regime, we have this kind of wonderful opportunity to actually see the classical quantum transition. And so I just wanted to kind of signal that to you so that you can stay aware of the fact that sometimes I might use phrases basically that belong in both regimes, and contextually their meaning should be clear. One thing that I've also tried to illustrate in this kind of cartoon diagram below is basically that I will loosely use the classical momentum and position variables interchangeably with the expectation value of the x and p operator. And again, from the context, it will be clear what I'm talking about. And from the correspondence principle, essentially, we expect these to kind of flow into each other at some level. And I'll show you that indeed that does happen in the relevant part, which is the first half of the introduction. Okay. So with that, let me get started. So what is quantum synchronization? For that, I have to first talk about what is classical synchronization, or synchronization as it's simply referred to. The classic texts on this are by Bikovsky and Palanov, so I have relied heavily on them, and I recommend them very much. And so this is a drawing via Bikovsky of the first illustration that Huygens made on this story. But instead of actually walking you through this, let me just show you the video, which is here, and I'll talk over it. So what you see here are several self-sustaining oscillators. So they're oscillators, metronomes, which if you do nothing, they basically will keep ringing, basically. They will keep oscillating. And as you can see, they're all out of phase. Now, what this gentleman is doing is he's placing them on a platform, two Coke cans or whatever, where basically the cans respond to the movement and hence can communicate energy from one metronome to another, one oscillator to another. And this phenomenon, given the right situations, which I will describe mathematically, is enough to synchronize the motion, as you can see here. So the motion basically becomes aligned. You can just visually expect this to be true. And this is basically qualitatively what synchronization is. And as you can imagine, this is a fantastic phenomenon. It's a phenomenon that has rendered great stability to a lot of phenomena in the natural world, and hence has become very, very important in our study of classical mechanics. So why is synchronization such a big deal, right? Before I get to that, let me just quickly emphasize to you that the kind of canonical method of thinking about synchronization is through a couple of examples. So, the Kuromoto model is the classic example. It's like the ideal gas of discussing synchronization. And what it is basically phase oscillators which are on a ring with a free phase degree of freedom. So this is this phase degree of freedom. And this phase degree of freedom, which I've just referred to as theta, this phase degree of freedom defines these oscillators theta 1 and theta 2. And they're coupled to each other basically in some fashion. And they're coupled to each other indeed in a bidirectional fashion. And so the classic example of synchronization basically asks, when do these oscillators come together and move in phase, and when are they basically out of phase with each other? And the answers, of course, depend on what the frequencies are and what these couplings Kij matrices are, right? So that's the rough story. This is the first sidebar of many sidebars. So this is a piece of information that I need you to know. And so I introduced this to you, so I apologize to the experts in the audience. What I need you to know is basically what a limit cycle is. And the limit cycle will become very, very important for the discussions that we're having. And so I define a limit cycle here. And what a limit cycle is basically, it's a fixed point in the radial direction. So here is an oscillator that actually can move in both the theta and the r direction. So it can change both its radial coordinates, so it can move up and down, and it can also move in a circle, basically. And so consider if the differential equation for the oscillator is 1 minus r square r, r dot is 1 minus r square r, then imagine what happens. What happens is that at r equals 1, you have something very interesting, which is if that r is perturbed from 1 slightly, which is that r is slightly larger than 1, then 1 minus r squared becomes negative, and there is a damping effect which pushes it back in. Likewise, if r is slightly less than 1, then there is a pumping effect which increases the r dot value and it pushes it back out. So this point, basically, this circle actually becomes a stable place of oscillation. And so this is what's called a limit cycle. It's a fixed point in the radial direction. And so these fixed points in radial directions are crucial to studying synchronization. So I just wanted to introduce it to you for those who might not know about about it. And so what is the big deal about synchronization? The big deal about synchronization is basically the fact that it's ubiquitous. It's everywhere in nature, right? So the circadian rhythm, heart's oscillations, the beats of the human heart, network synchronization, fireflies. So the variety of examples in the natural classical world where synchronization is prevalent and has a positive effect in stabilizing and creating functionality for either the organism or the superorganism or a network, an artificially constructed network. This is profound, and so this is the exciting and interesting thing about it, and the reason why many of us have started studying synchronization in the quantum region. Yeah. So with that, let me also take the opportunity to introduce one more variety of synchronization. So the ubiquitous kind of ideal gas example is the one that I showed you before, which is the Kuromoto model, where you have the Ki-J matrix, which couples I to J and J to I. Whereas this is basically the standard example in the quantum synchronization universe. And so it's called entrainment. And entrainment is where you basically have, let's say, I'm taking the exact two same examples, theta 2 and theta 1. But theta 2 is a much, much heavier oscillator. So what that means is theta 2 doesn't like to respond at all to theta 1, because theta 1 doesn't have enough, basically, momentum to pull on theta 2. And so theta 2 is oscillating at whatever frequency that theta 2 is oscillating, but theta 1 responds to the motion of theta 2. And so this is a unidirectional coupling, and this is exactly like basically taking some sort of a cantilever and driving it from the outside, so with an external oscillator. And so the external oscillator here is played by theta 2 naught. And so what initially when we started, what we wanted to do was either think of kind of these kinds of examples. So in the literature for the last 10 plus years, 15 possibly, there have been nanomechanical and optomechanical resonators, which are in part mechanical resonators, right? Just like this cantilever, but are in other parts quantum mechanical in nature. So if you get this mechanical motion down to its ground state, or near its ground state, then it starts exhibiting quantum features. And so this is very exciting, because what that means is that you have for the first time the capacity to investigate what happens to nonlinear physics phenomena, like entrainment, like synchronization, so on and so forth, but in the deep quantum regime. And so here I've also envisioned basically, let's say maybe coupling some qubits onto it by embedding them into the resonator, into the nanomechanical resonator in this example. So this is the kind of physics that I want you to imagine when we're discussing synchronization.
Oh, sorry, Sai.
So
I have a quick question for you. So you just spoke about these sort of nano-electromechanical resonators where you have certain qubits and the mechanical oscillator, right? What is exactly you're referring to now? What is this theta variable in this quantum system? What does this? So is this the qubit that you're looking for?
No. So what you would do is you would the resonator basically would have to be made anharmonic, and if it's an anharmonic resonator, then you can map it onto a VDP or a Stewart-Landau, something like that, and then you have an anharmonic oscillator which can exhibit synchronization, coupled, let's say, to qubits, quantum mechanically coupled to qubits, and then you can have all kinds of fun with that.
Okay. So, but it's still the oscillator.
It's still the oscillator.
Okay.
Yeah, in this example.
Okay.
I will show. I mean, the main part of my talk will not be about oscillators, so it will be about other things.
I see. Thanks a lot.
Okay. Okay. Shall I continue?
Yes, please.
Okay. Yes. So so let me just put a reminder here. So the reminder to myself to kind of clarify to you is that, one, we're going to deal with a lot of dissipative systems here, because just like kind of real mechanical resonators, they're going to have that have dissipative processes, both pumping and damping dissipative processes. We'll be interested in dissipative processes which are basically quantum mechanical in nature. So we need to start making discussions in open quantum systems language. The second point I want to emphasize to you is that we're going to deal with synchronization, which needs a phase reference. So this sounds like a silly point or a trivial point, but let me just emphasize this, because this has caused some amount of controversy in the literature. The important bit here is that immediately what I need to introduce to you is a quantum optical phase space representation, so that we can make this discussion about the phase that is being synchronized, which is exactly what Juza's question was a second ago. And the third is just a gentle reminder that we will always be interested in steady states of the master equation. So what that means is that you set up an oscillator, you set up a network, whatever, and then you just leave it alone and you see what happens in the steady state. So these are the three things that I just want to post as reminders. And with this, basically, I go to my second sidebar. So these are all sidebars that are self-contained, so that I can carry anyone who doesn't know this with us. And so this is basically the fact that to make discussions in the open quantum systems language, I need two constructs which I present to you right now. The first of it is basically what is called a density matrix. A density matrix, one way of thinking about it, which is in this kind of dotted box, is that a density matrix is simply a mapping of a wave function to the outer product of a wave function. And in fact, it's just the convex mixture of such outer products. It's also a linear object that you can use inside Schrodinger's equation. The other, go ahead, Susan.
There's a question from Sarika. Sorry for that.
Hi, Sai. So have you already introduced the definition of quantum synchronization? So classical synchronization, we understand. So phases are moving together. So
yes.
What is the definition of quantum synchronization? So you are going to introduce.
Yes. It's again some sort of phase localization, and I will quantify it in a second.
Okay. Thank you.
Yeah. Okay, so let me just quickly walk you through density matrices and Limbular equations, if that's something that again someone needs a quick introduction to. Which is that there are two ways to think about it. One is that you can think of it as convex mixtures of pure states, and and just convince yourself that all of the linear quantum mechanics follows through. There is another way which is actually slightly more pleasing to one's imagination, which is to take what's called the system environment approach. So here, basically, I have a pure state. So I say, look, I don't know about my little atom maybe interacting with gas particles that are in the chamber, or they may be interacting with electromagnetic fields, the stray electromagnetic fields. But if I close the box somewhere, if the thing that I'm interested in, my atom, is my system, and the electromagnetic fields or whatever else is the environment, if I draw a box around the whole thing, then that's a closed system. And closed systems, I learned in Quantum Mechanics 101, have wave functions. And so yes, so if you take the pure state of the universe, so which is the system plus the environment, and you write it essentially in some special basis, then within a couple of steps, you can convince yourself that this formula is correct as well. And so I will just take it for granted from now on that I can talk about density matrices. But of course, I'm happy to elaborate offline if anyone wants any clarification. So I'm going to deploy density matrices whenever I want to talk about open quantum systems, because not only do I have the system that I'm interested in seeing synchronization in, I want to see it coupled to an environment, and the environment must be able to either feed it energy or pull energy from it in a linear fashion, in a non-linear fashion, exactly like we've come to expect from classical synchronization physics. So for all of those reasons, I basically need an environment sitting around. Not always true. For instance, the Kuromoto model is a closed system, but for all the examples I'm going to talk about, this is true. So that's number one. Number two, in this sidebar that I want to introduce, there are three of these. The second part of the sidebar that I want to introduce is basically what is called a Limbular equation. So I will flash these Limbular equations later on, and so I want to make sure to clarify what they are, so they just don't sound mysterious. You can derive them basically from starting from this exact approach that I've outlined here. So all you are committing to, pedagogically speaking, all you are committing to is that the universe has a wave function and the universe has a Hamiltonian. And with a ton of approximations, which are very well known, I'm happy to talk about them. You arrive at an equation like this, and the equation basically, the only thing I want to point out to you is the following, which is that the equation is trace preserving. So if you just take the trace of these operators L, rho, L dagger minus half, then you can convince yourself the algebra is here, that the trace is 0. And so the shorthand way of writing these objects is basically this dl of m. So dl of rho, which is what you will see when I discuss thermal Limblarians later on, is just given by this form. And all I need you to be happy about is, one, that they are coming from a system environment approach, and two, that they're consistent descriptions of of these kinds of open quantum systems in some very heavily approximated regime. So the third piece of kind of physics that I need is from quantum optics, and they're basically what are known as Wigner functions. So Wigner functions are phase-space quasi-probability distributions, and they're, the formula for them is given here. They're very well-known objects, so I'll just skip over them. I just wanted to basically flash just in case somebody didn't know. The only piece of information that I actually want to make sure that everyone has with them is that instead of writing the Wigner function, I could have written the density matrix. And instead of writing the density matrix, I could have written what is called the Q representation function, the Houssy-Mikano Q representation function. And the Q representation function is basically the expectation value of the density matrix in a coherent state alpha. So both these Q alpha and W beta are both basically quasi-probability distributions, which means they are probability distributions, but the Wigner function, for instance, can become negative. And they capture quantum mechanics, but they also seamlessly transition into classical mechanics. And so this will become important in a couple of slides, because I'm going to show you classical expectation values and quantum mechanical expectation values on top of each other. And so when we basically talk about classical quantum correspondence, I just need to bring and the picture for the Q representation functions, they always are positive semi-definite, and they look very, very, very nice, satisfying to the eye. Okay, so with all of that, let me get to the first point about quantum synchronization. So quantum synchronization. So in this paper, which is Walter Bruder and Kemp, what the authors did was they considered basically this modified version of a Van der Pol oscillator. It's actually a Stewart-Lambda oscillator in the complex plane. So beta is basically a complex variable. And what they showed was that if you consider this equation, which is a Limbular equation that I just flashed a second ago, with the Hamiltonian, which is basically written in terms of some detuning delta times n, plus some strength f times y, and I'll explain delta and f in a second. And if you calculate the expectation value of the annihilation operator, so trace of rho a, which is this beta equation, then you end up with this equation, which is given in black, right? So so this is interesting basically, because what it means is that at the level of expectation values, with some approximations again, at the level of expectation values, this equation, which is a classical mechanical nonlinear equation, is basically being captured by linear quantum mechanics, right? So you can see the mod beta squared beta, which is the inherent nonlinearity that is coming in. So let me explain just 1 second, take 1 second and explain these two numbers, delta and f, because they're very, very important. Delta is basically the detuning of your natural resonators, the drive frequency from the natural frequency of the oscillator. So always in synchronization studies, what you have is you have a resonator whose natural frequency is something, let's say 5 megahertz, and then you're driving it off resonance basically. And if the resonator basically responds and shifts its frequency over, then that's synchronization, right? So let me just go back and make this point in the with the diagram. So if this resonator is at 5 megahertz, and I basically drive it basically with an external oscillator off resonance, and the resonator responds off resonance, actually locks onto that external oscillator frequency, then that's synchronization. It's different from simply driving a linear resonator off resonance, and I'll explain that in a diagram shortly. Okay, so just to summarize, delta is the detuning between the driven frequency and the natural frequency, and f is the strength of the drive. And what Walter Bruder and Kemp pointed out are two figures here. The details are entirely relevant. The only thing I just want you to take away is that this black circle that you can see inside this figure is the classical mechanical, is the solution to the classical equations. Because remember that this Van der Pol oscillator is just a nonlinear oscillator. It's being driven at some frequency omega drive with some strength f, and that the quantum mechanical analog of it is sitting here. It's in the difference between the in the frequency of the drive and the frequency of the oscillator, and the f is again the quantum mechanical analog of the frequency, the strength of the drive. And so what Walter Bruder can point out is that this red coloration that you're seeing is the Wigner function. It's essentially a color plot of the Wigner function as a function of a position and a momentum. Position is defined as basically the real part of the alpha that I defined a second ago, of beta, and P is defined as the imaginary part, basically. So they're just the real and imaginary, the two quadratures of the electric field. And what I want you to see is that there is one regime. Just a second, user. Yep. There is one regime where there is complete locking. There is complete agreement between the classical answer, which is the black circle, and the kind of the center of this thick Wigner function. Whereas there is another regime where basically they're driving it where the agreement was not so great. So it's quite close, but it's still not so great. And this is something that I just want you to keep in mind. Go ahead, Joseph.
Sorry, we just have a question from Jungyun. Jungyun, you can go ahead. Sorry, we can't seem to hear you, Jungyun. Okay. We can't seem to hear him, but sorry, let me ask one quick question till the time he probably sorts out his issue. What is Y here, Sai? So in the Hamiltonian, I believe
sorry,
N is just A dagger A, perhaps? This is your number operator?
Yeah, Y is a typo. Y is just P.
Sorry, I didn't quite catch you there. Y is what?
Sorry, Y is just a typographical error. It's just the momentum, P.
Oh, I see, it's P, okay. And can you just elaborate a little bit more? Because you said there are two different regimes in panels A and B, right? Is this a quantum regime somehow, the panel B and...
Yeah, it's the difference between... It's the difference between having driving it in the quantum regime and driving it in the classical regime.
I see.
I believe I have a slide for this. This is the very next slide. So I'll just explain that in that slide. Yeah.
Okay, I think we have lost.
Do we have the?
I'm not sure.
Okay.
Sorry, can you hear me?
Yes, we can hear you now, Jungyun. Yes.
Okay, so I changed the microphone. So my question is, what's the microscopic origin of this master equation? I mean, how do you induce this nonlinear coupling, like A squared term?
Yeah. So several answers here, I must say. One is that in several of the early papers that were written, this the argument was basically that, look, we're just trying to study this phenomenon. So here is a toy model, and let's take it at face value. But at the same time, I must say, both Walter Bruder-Nunenkamp and this other paper by Lee and Sadetko, both of them tell you actually how to generate the nonlinearity. They give you a plausible way to generate the nonlinearity. So I forget which of these I'm going to quote now. I believe it's Lee and Sadetko. What they do is they say, if you take a trapped ion, basically, and its motional degrees of freedom are the A, then by using a red detuned laser and a blue detuned laser, you can basically get incoherent transitions. And if you basically detune one of the lasers to a single photon transition and the other one you detune to a 2-photon transition, then you should be able to derive this, at least you should be able to see that this is true. Now, having said this, so this is part one of the answer that I want to give you. Part two of the answer, I want to clarify by saying that people have attempted basically microscopic derivations. So my colleagues at CQP themselves have papers where they've attempted microscopic derivations of these things, and they get very, very messy, basically, because you have Juza is in fact the expert on deriving master equations here, and you have huge amounts of complication trying to take appropriate limits that are required to actually derive the master equation. So whether this, whether this is a kind of completely valid master equation or not is something that I think is very system dependent. It depends on basically things like what the spectral Bach density is, and whether there is enough modes there basically to either support the master equation derivation or to reject the master equation derivation, things of that sort. How weak is the weak coupling? And so it becomes a question of a lot of details that I'm happy to go into later.
Okay, thank you.
Okay. Okay, so let me just continue with this story. So again, what I want you to notice here with this kind of synchronization of the quantum versus classical regime, just to bring that analogy out, is basically that there is a linear pumping here. So this is the dissipator that incoherently puts one photon into the system, or one phonon into the system, and a nonlinear damping here, which basically pulls two photons from the system, basically. And so this linear, nonlinear competition is actually very well known. It's in Tchaikovsky, it's in all of the standard textbooks on the story. And the other, and the interesting bit about this whole physics here is, in fact, the fact that you can make a transition from the classical regime to the quantum regime. So look at what gamma 1 and gamma 2 are. Gamma 1 and gamma 2 are the rates attached to basically the linear process and the nonlinear process. If gamma 1 is much larger than gamma 2, so this is this, if you're in this regime, then what happens? What this basically means is that you have the linear pumping dominating over the nonlinear damping, which means that a lot of photons are in the system, or phonons are in the system. And what it means is that the action over h bar is very large, and it's very classical behavior. And that's the regime that was in the first figure. Whereas the other regime, basically, where the nonlinear process is very strong, pulls a lot of photons out of the system, and it basically leaves it close to the ground state, and that's this guy over here. And so that transition you can actually observe going from classical to quantum, and that's something that's also very interesting. Yeah. So one thing that I will make a lot of use of, and so I want to introduce it to you, is measuring is a way to measure classical synchronization and hence quantum synchronization. And so the way to do this is actually to plot a diagram, essentially either like this or like this. So this diagram, this is from Tchaikovsky's book. This diagram, what it shows you is, it says what happens, in what way is a driven nonlinear oscillator, which is exhibiting synchronization, different from just a linear oscillator that's being driven. And the difference is basically this little flat region here. So what happens in this flat region, so this was the example that I said before, 5 megahertz or whatever. And so that's the natural frequency of the resonator. And I'm driving it off resonance. So I'm driving it somewhere here. And what's happening is that instead of just weakly responding at my natural frequency to the external drive, the hallmark of synchronization is that there is a complete phase locking, frequency locking basically, and then there is oscillation basically at the correct frequency. After a while, so suppose I drive it not at 5 but at 4.5 or 4.3, it responds. But if I drive it at 2 basically, which is on this side, or at 7, which is on this side, then maybe my natural oscillator says, look, that's too much detuning for me, and I can't keep up. And then it basically uncouples and goes back to its own natural frequency. So these are some weird units that we don't need to worry about. So what happens to this little band when this little region of synchronization, when the strength of the drive is increased? What happens, of course, is that the region becomes bigger and bigger, and this triangular shape that you see here is what's called the Arnold tongue. So whenever you see the Arnold tongue, it's the signature of quantum synchronization or classical synchronization, because what it's basically saying is there is this flat region where you see stable locking basically to the drive frequency. Right? Okay, so with that, let me just point out just a couple of different things, which I thought that I'll also give you a little bit of a review here on what synchronization is being thought about in the quantum regime.
Sorry, just to interrupt you, we have another question.
No, absolutely.
Yes, Rohit.
Yeah, hi, Sai. So you talk about this Arnold tongue,
yes.
But this is for driven systems, right? So if you don't have any driving, is there any notion of Arnold tongue there?
You can do it with the coupling strength, which is, I think, one way to do this. But let me just say, there's going to be very formal measures of synchronization that will also come. So so you can. But yeah, I mean, so this G could either be the drive or the coupling. Both work. In fact, this example right here is where is the thing? Yeah. So you can see this example, Rohit, right here, which is that the coupling strength G. So let me just explain this example to you. Which is, it's 2 cavities with 2 atoms, 2 qubits inside, 1 qubit inside each cavity. and then they are coupled to each other by this coupling G. And what you see is an Arnold tongue in the mutual information as a function of G. So the driving strength is replaced by the coupling strength, because again, go back to the bidirectional versus unidirectional. All I did basically was I just made one of the oscillators have very large inertia, but they're still coupled according to the same, the same physics. And what happens is that that coupling basically becomes the drive strength.
Okay.
Yeah, so that's the way I rationalize that argument.
Yeah, but what are the quantities you can look at it? What is the criteria? I mean, here you have looked at the mutual information, right? And so what are the quantities you can look
there are
upon?
a ton of you can look at very many things. Let's just postpone this to the discussion session, because I'm happy to give you a longer answer.
Sure.
Yeah. Okay. So again,
sorry, Sai.
I just want to point out. Yes.
Sorry, we have another question. So, Sarika.
Quick question. What is this lambda? What is x-axis here?
It's not lambda. Sorry, it's detuning delta.
Oh, this is delta. Okay. So y-axis is coupling strength. So what is this delta? If you can again, this is the difference frequency, is it?
Yeah, it's the difference frequency between the two. I think. Yeah.
Yeah. Okay.
I'm pretty sure.
Yeah. Thanks.
Yeah. So same. It's the same story basically as classical oscillators. Okay. So So I just wanted to quickly flash basically that in the quantum in the quantum setting already we have some very interesting leaps that were made. One is that mutual information is a very good measure, because what mutual information in fact does is it's a very nice measure that is present both in classical information theory and in quantum information theory. So classical mutual information is defined almost identically, it's identically to the quantum information theoretic measure. And so mutual information also shows an Arnold tongue-like behavior, and this was something that was observed several years ago. Likewise, quantum discord also, sorry, this should say quantum discord here. Quantum discord also exhibited an Arnold tongue-like behavior, and so I'll just leave this here for those who know what discord is. Again, I'm happy to take this up in the discussion session. Okay, so that brings us to our part of the work. So now what happened was that for various reasons, basically people started wondering what happens to synchronization if you basically move quantum synchronization from this kind of semi-classical universe that we are talking about till now, where you can both you can traverse the classical quantum transition very easily and move it over to basically finite dimensional quantum systems where there is no quantum analog, there's no classical analog. Sorry. So how do you discuss quantum synchronization for finite level systems? This was the conversation that people came upon a couple of years ago. So let me re-emphasize for those who are not familiar with synchronization. Again, I just need you to take away 2 points now. One is that synchronization requires the existence of a limit cycle. Right? There must be this angular degree of freedom that basically, there should be basically in the radial direction, there should be a stable kind of circular orbit there. And the other condition that is required is that the angular degree of freedom should be able to exhibit locking. It's again a very silly point, but I should be able to see when I'm doing nothing that the angular degree of freedom is going round and round. And when I lock the oscillator to an external drive, for instance, then it should not be all over phase-space, but it should be basically localized to some region. So I must be able to observe all of these things in the classical and the quantum region. So already this precludes basically qubits, and so this is the only point I want to make to you. And so let me elaborate what I mean by that. So if I have a qubit, basically, what is a qubit defined? What is a qubit limit cycle going to be defined as? It's going to be defined basically as a diagonal distribution, right? Why is it going to be defined as a diagonal distribution? Because if I don't define it as a diagonal distribution, then every angle that belongs to the qubit degree of freedom is locked away. So so theta is defined if I choose the populations to be, let's say, 1/3, 2/3. And if I also basically assign the phase here, then basically the relative phase here, then basically there is nothing to synchronize. There is no angle to synchronize. Now, the crucial observation here is that the a phase variation, let's say in the 1 degree of freedom, which is just e to the minus I phi, is a gauge degree of freedom. It just gets gauged away, and you can't see it, right? It's unobservable. It's physically unobservable. And so the argument basically is that phase space-based definitions of limit cycles don't allow for qubit synchronization, because qubit synchronization would demand that you should be able to see the limit cycle, and you can't see the limit cycle. And I just caution basically that there are some counterpoints on this in the literature, and so I'm happy to refer you to them. I don't lean on those counterpoints. I understand the counterpoints, and I don't agree with them. And so I'm happy to discuss why that is. Okay, so if not qubits, where do we go? We go to qubits, of course. So qubits are 3-level atoms, and so here is an initial paper by Bruder again, Alex Roulet and Bruder, and they basically considered a 3-level atom, which was basically has this -1, 0, +1. I will use a different notation in a second, but let's just go with this for now. And what they considered was basically two dissipators. A dissipator that takes you from -1 to 0, so it only takes you from -1 to 0, and a dissipator that takes you from 1 to 0. So if you're in this state or this state, it just pumps you to the middle. Basically. That's the two dissipators. And so, of course, the crucial point here, the crucial difference between this and a qubit, is that this limit cycle is now observable. It has a free phase, which I will discuss in a second, and it is observable. So, so this undriven 3-level system, it naturally settles down in the middle, and it is indeed observable. Jusa, do you have a question?
Okay. No, it's all good. Thanks.
Okay. Yeah, I heard the microphone go off. So, yeah. Okay. So, so where is the degree of freedom? Where is this free degree of freedom? So the free degree of freedom actually is very easy to see if you actually define the Husimi-Kano Q representation function for the 3-level atom. So this is a bit of a technicality if you're not in quantum optics, but let me just walk you through it anyway. So the coherent states basically are defined essentially as these exponential. So you can define it using an Euler angle type technique, but basically they're defined as these displacement operators acting on either the highest state in the algebra or the lowest state in the algebra. And so canonically, it's the highest state in the algebra. And taking this highest state in the algebra, you can define basically a general coherent state, N2, which is given by some phi and theta degree of freedom. And if you take this N2, which is also called alpha, I'll interchange between these two notations, then basically this expectation value of a density matrix basically has these two angles, theta and phi, right? And now, if you look basically at what the Husimi-Kano Q representation function is for a 3-level atom, it's just proportional basically to the expectation value of the density matrix in the number state n, which is given by these two variables theta and phi. So this Q basically has two angles theta and phi, and as we will see, the phi degree of freedom is in fact free, right? To see that, what I need you to do is basically look at what happens if I take this n degree of freedom and I take a bare Hamiltonian, which is like SZ, right? SZ here is just 1, 0, -1, right? This is SZ. So SZ is just 1, 0, -1, and so if I take SZ as the bare Hamiltonian, so it just defines an equally spaced 3-level atom, which is what Bruder and Roulet were considering. And I basically take my spin coherent state and I displace this with my bare Hamiltonian. What am I doing physically? I'm asking, what is the evolution that is generated by the bare Hamiltonian? What is the quantum state? What it does is it actually just simply moves phi to phi plus omega t, right? You can just check this from the algebra, combine these two. And so what this means is that if you plot basically the Husimi Q representation function, so this is a Winkel triple plot of the Husimi Q representation function, what you see is that there is 1 degree of freedom, this flat degree of freedom here, where the color does not vary at all, right? And this is basically the omega, the phi degree of freedom. It's the free phase. So along this phase, the oscillator keeps rotating, and it doesn't actually make a preference of where the angle is. Whereas along this direction, there is a strong preference. So let me just get down here so that you can see. So you can see that there is a strong preference in the strength of the Husimi-Q representation function of localization around this value, which is at the center. But along this direction, there is absolutely no phase preference. So in that sense, it's an observable, it's a phase that is free, and it is an observable phase, because you can, of course, in a 3-level atom check whether your quantum system is in the middle level. So, so for that reason, basically, Roulet and Bruder suggested that the 3-level atom is the simplest quantum system that we can synchronize.
Sai, sorry, a quick question.
Yes.
If you would, instead of a 3-level, if you were to take an n-level atom, would that immediately mean that you would have some n minus 1 or n minus 2 degrees of freedom, where you would get some complicated n-dimensional limit cycle?
Yes, in fact, you'll get a more complicated object. I'll actually generalize this in a second. We generalized it in the paper that I'm going to describe.
Okay, perfect.
So I'll generalize it in a second, and then we can look at it.
Yeah, perfect.
Okay, so with this kind of, let me move forward. So what they did, so these are the two dissipators that I just told you about. What they did was, they drove basically both of these transitions, so the 0 -1 transition and the 1 0 transition, with a SY operator, and the SY operator couples everything. And the SY operator appears with a strength epsilon and a frequency omega d, which appears in the detuning. So exact same story as before. And now what they did was they defined a measure of synchronization. So the measure of synchronization is to simply check whether the Husimi-Q representation function, which is plotted here, whether the relevant degree of freedom, which is the free phase degree of freedom, whether that is indeed free or if it is locked. If it is free, then it is uniform. And if it is uniform, basically, then your integral should be easy to do. The integral produces a number which is 1 over 2 pi. So if you just define a synchronization measure, which is the integral over the fixed degree of freedom, which is the theta degree of freedom of the Q representation function, and then you subtract out the uniform part, then this is a measure of quantum synchronization, S of I. And this answers, in part, the question that Sarika was asking earlier. And now what you can do is you can take this S of phi and you can find the maximum value of it with respect to phi, and you can plot this object. And what you will see is an Arnold tongue, which I will show you. I don't know where it went. Oh, okay. I seem to have made it disappear somewhere. Sorry. So they should. So what they did was they plotted this, and they see an Arnold tongue. I don't know why it doesn't appear here. And so with that, let me go to my work now. So this from here is basically Naufels, Mikhal's, and our work. And so what we wanted to do was we wanted, of course, think about synchronization, but think about synchronization inside of a quantum technology platform. And so the oldest, known quantum technology platform, to misuse that phrase a little bit, is just a laser. It's a maser. And so on the right-hand side, I've basically presented to you a maser, 3-level maser. So it's the simplest maser that you can construct. So you do a population inversion, and then you, when you basically make this transition, you see an emission here. So what we wanted to ask was, what if we treat this 3-level atom as a synchronizing quantum system? Can we understand the laser power output that is coming out, or the maser power output that's coming out, in terms of synchronization? Can we understand, can we collect all of this physics together in one place and understand it in terms of synchronization? Additionally, we wanted to also try and investigate what happens to the relationship between synchronization and quantum thermodynamics. So what we did was we considered a thermal maser. So a maser whose energy levels are driven not by actual pumping, but by thermal transitions, TH and TC. So that's the kind of setup that I wanted to think about. This is a very famous example, basically, by Scoville and Schultz-Dubois. So I'll just explain that in a second. So before that, I just actually want to just give you a one-line simplification of what heat and work are going to look like in this story. So, so I refer you to this very famous paper by Lichky. And what Lichky's argument was he said, let's consider just the expectation value of the Hamiltonian, which is what we define as the energy. And if you take the variation in the energy dE, then you can either vary the Hamiltonian or you can vary the density matrix, right? It's dH times rho, rho times dH. But what is DH? DH basically means that the Hamiltonian is being varied, which means that the Hamiltonian is no longer constant in time, which means something is happening from the outside. And so what Alichki argued was that you can assign that to one. And hence, by the first law, basically you can assign this to heat. So I warn you, not the least because Juza is in the audience, that this argument is only valid in weak coupling, Markovian, blah, blah, blah setting. So the moment you step out of this, this becomes very, very complicated, and you have to actually pay a lot of attention as to how you define heat and work. Thankfully, we are studying perturbative synchronization. So synchronization with very weak coupling, very weak driving or very weak coupling. And so in these regimes, basically this definition is sufficient and we can just move on. There is one additional complication which I will mention in the right place. So with this, let me introduce you to the Scoville-Schulz-Dubois thermal engine. Basically, their argument was that the Maser efficiency is simply the difference of the frequency of transitions omega 3.2 divided by the difference in the frequency omega 3.1. And what Scoville and Schulz-Dubois were saying was, they were saying, look, actually this is just a heat engine, because you don't need to do the population inversion by hand. If you just have a very hot bath coupled to 3 and 1, then this is NH gamma H here, and gamma H NH plus 1. Then what happens is that this transition basically, let's say it's an infinitely hot bath, so 1 and 3 are equal population, 50-50, but there's more physics happening here. So maybe it's not 50-50, maybe this is 49, or 48, and then this is 51. And that rest of the, 1% or whatever is in this cold bath, is in this level 2, because this is a cold bath coupling, 2 and 1. And so it pulls almost all the population down to the ground state and leaving very few. But what that means is this is 1% and this is almost 50% of the population inverted. And so you can get a transition out of this by only coupling everything to heat bath. So this is the basic setup that I had here. So this is how you couple 2 heat baths to a 3-level atom, and you still make it work as a laser. So for time sake, I won't go through this argument, but if you just run through this slide here, you can very quickly convince yourself that the Maser efficiency is bounded by the Carnot efficiency. And so this was the major finding of the Scoville-Schulz-Dubois paper. What we wanted to do was do the exact same thing. But let me just point out that to do that, we need basically a Maser efficiency which is basically manipulatable, because omega 3.2 is the difference of frequency between 3 and 2, and omega 3.1 is the difference of 1-3 frequency. In the Bruder-Roulet paper, they had an equally spaced 3-level atom, which means that 3.2 is exactly half of 3.1, which means that the efficiency is always stuck at a half. And this is not good. So what we wanted to do was generalize this. So to generalize it, we have to generalize basically the quantum synchronization itself from just an equally spaced 3-level atom to a larger space. And so, so we started by writing the master equation down, which is just presented here for completeness. And we defined the generalization of the coherent state by basically just referring to some very nice literature that exists. So Kuromoto's classic paper from 2000, and Manu Mathur and a couple of papers there. So the argument here is quite simple, but I'll skip it because I noticed that I only have around 10 more minutes. And let me just say that this coherent state can be generalized, and you have 4 angles. Let me explain what they are. One angle, theta, simply measures how much population is as opposed to 2 and 3. So the square of cos square theta is simply 1 minus this object. One angle psi measures how much population is there in 2 versus 3, and phi1 and phi2 measure basically the phases relative to basically the ground state, let's say. So that's the way to imagine why there are 4 angles here. And so that explains in part the question that the other person was asking, which is that if you go into higher and higher dimensions, then you have this proliferation of angles, and you have to pay careful attention as to what you want to say about it. So now you can define a Husimi Q representation function. Of course, just like before, you have a coherent state that is completely general for 3-level atoms. So this is the full SU3 coherent state. And this SU3 coherent state, you can take the steady state density matrix and you can define the Q representation function. It will have 4 angles. The population ratios theta and xi, and the relative angles phi1 and phi2. But you can again check what happens when you basically when you apply a general diagonal Hamiltonian Hamiltonian, which is what a free Hamiltonian will look like. General diagonal Hamiltonian will actually change theta and xi, but not phi 1 and phi 2. So you integrate out theta and xi and you remove basically the constant part, and that's the measure of synchronization. So same as before, basically. So now what I want to show you is basically the plot of this measure of synchronization as a function of the detuning. So the detuning, let me just back up 1 minute. The detuning is basically sitting in this Hamiltonian. Did I write it down somewhere? Oh, well, I guess I did. So the detuning is basically, it's in this diagram. So this detuning is the detuning between the laser field that is applied only to the 2-3. It's the detuning between the laser field and the actual transition. And the strength of the drive is epsilon, right? So epsilon and delta are what are plotted here on the x and the y axis. And so delta, epsilon on the y axis, and the maximum measure of the synchronization S of phi 1 comma phi 2 is plotted on the z axis, on the color plot. And what you can see is basically a very clear Arnold tongue, right? So step 1. So now the question is, why is this Arnold tongue appearing? We have to understand the Arnold tongue, we have to make sense of it. So we went back and we showed that basically this quantum system actually has a synchronization transition. So this is, in fact, this is the proof. But what we wanted to also understand is whether this has any relationship to quantum technologies. So what we did was we plotted the coherent power output by this thing. So this is not the Lichky definition, it's a slightly different definition, and I will get into it if you want. But the power output, you can see, also has a very clear Arnold tongue behavior. And so this is very, very crucial to understanding the paper, because what this basically signals is you have something very interesting happening where synchronization-like behavior, which was only ever seen in classical systems and was seen in quantum systems only in kind of proof of principle experiments. There are 2 of them now out in the literature. What we are arguing is that you could actually see them in any laser. You switch on any thermal laser and you just detune it, and the moment you detune it and you capture the power output, the coherent power output, you'll be able to see this, or the incoherent power output, in fact. You'll be able to see this. And so how do we understand? So this is basically, in one fell swoop, is claiming that, the same thing that we've known from classical mechanics, which is synchronization, is ubiquitous. Not only is it ubiquitous, you can see it in every laser in the universe that you get to look at. So how do we understand that this Arnold tongue behavior is happening and that power is somehow related to synchronization? What's the relationship between thermodynamics and dynamics? This is the question that I want to answer in the next couple of minutes. To get a hint, what we plotted was basically what is called the L1 norm of coherence. It's a resource theoretic measure of coherence. So this is another hint that basically coherence is also doing something very interesting and Arnold tongue-like. And so the story is basically here. It's what it is that synchronization drives coherent behavior in a quantum system, and coherent behavior drives the power. To make that argument basically solid, to kind of lock down that argument, let me just show you the exact same equation I showed you before. So there were 4 angles for the 3-level atom. 2 of them were integrated out, and then the constant was removed. That's the measure of synchronization. If I write it out as to what it is, it's basically just the real parts of some phase e to the I phi times some element of the density matrix. You can just calculate this. It's a simple calculation. So if you maximize this, basically what you can see is that the maximum is actually, in fact, just the L1 norm of coherence. On the other hand, the power is basically related to the imaginary part of the steady state, the 2-3 steady state element of the density matrix. And so what we can do is we can relate. So already it's very clear that the maximum value of the coherence, which is what is plotted, is related to the L1 norm of coherence. And the second thing that is very simple to see is that the power and the S max are related to each other actually by this inequality constraint. So the power can be shown to be less than or equal to something that depends on the size of the drive times basically the S max. Now, this is just shown in a figure here. So what you see is basically variation of basically the variation I forget now. I think this is so sorry. These are the 3 measures here. So the variation of the measure of synchronization, and this is the power. And what you see is the variation of these two things as a function of the temperatures of the baths. Sorry, as a function of the temperatures of the baths here. And so what you see is basically, as you go from 0 to some positive value, you cross basically the Carnot limit. And when you cross the Carnot transition point, engines become fridges. This is actually well known in the thermodynamics literature. And what you see, this engine becoming fridges, is basically also exhibited here. But what you see is that the synchronization measure goes to 0, the power goes to 0, and the power is exactly 0 at the transition point of which is given by the Carnot limit, right? 1 minus eta equals Tc over Th is simply eta is 1 minus Tc over Th. It's just the Carnot. It's just the Carnot efficiency formula. And what we're seeing is basically that the blue, which is the synchronization measure, also goes to 0. So what that is signaling to you is basically that the synchronization measure is locked on to the thermodynamics of the physics of the system that is that it is trying to observe, even though it knows nothing about thermodynamics per se. It's just a synchronization measure that we drew from from these other discussions that we've had before. Okay, so I'm at the 57-58 minute mark. So let me just conclude briefly. So what hopefully I've given you a small glimpse of is the interplay between dynamics and thermodynamics. I think this is a very, very interesting area for us to hang out in, and I know Juza's done some work here, and I'm happy to kind of talk about this more. Synchronization and quantum synchronization measures for 3-level systems I hopefully introduced to you, and I also showed you basically that the limits of the performance of thermal engines can be set by quantum synchronization in regimes, in places where synchronization is meaningful to define. So if you have something where all the physics is linear, then, well, synchronization is irrelevant. If you have a regime where basically it's very heavily driven and the driving strength is very strong, then synchronization again is somewhat has to be carefully discussed. So if you stay out of those regimes and you discuss only the regime where basically, which is of interest to many, many experimentalists and many of us as theorists, I think in that limit, basically, synchronization and quantum thermodynamics have a lot of interplay with each other. And so we're right now working on extending this to coupled systems and so on and so forth. And again, I'll leave that for the discussion session. I just want to kind of thank you for your patience. I understand that this must be a slightly kind of complicated talk because there is a lot of kind of ground to cover in terms of various different fields. So I hope that I've been able to do some sort of a job in trying to introduce these various aspects to you. I'm happy to take questions.
Great. Thank you so much, Sai, for this talk. Let us all please thank our speaker first. Okay. If there are some quick questions from the audience, Sarika, go ahead.
Yeah, hi Sai, it was very nice talk. It's not a quick question, but so like in classical synchronization, you have the stability analysis around the synchronized state, and that confirms whether synchronization exists or not. Here I understand that you get a null tongue, which is a signature of quantum synchronization, but do you have some quantum manifestation of stability analysis?
No, for the steady states, we analyze. You can again analyze basically whether you have a. So first, Sarika, is that you have to establish the existence of a stable limit cycle, right? And so that is basically true for both quantum and classical. And so we can actually show that there is a stable limit cycle in all of these examples. And so then, when you kind of drive on top of it, then you basically see the synchronization behavior.
Okay, thank you.
Okay, Kodo, go ahead. Okay, I unmuted you. Go ahead.
Yes, thanks. So thank you for your talk. And could you show me the slide where there was like kind of flat interval and then the flat interval was increasing?
Sorry, what slide?
I mean, it was like almost like in the beginning.
Okay, let me.
Maybe when you're talking about Arnold tongue, is this what you're referring to, Kodo?
I will just say, wait. Yes, this one.
Okay.
So I mean, there was a flat interval, right? This, and then it somehow it keep increasing in the right figure. So I mean, how come it's increasing again? By changing what?
Sorry, are you asking? I didn't hear a particular phrase that you used. Are you asking what this is?
I mean, so there's a flat area, right?
Yeah, there is this area, flat area, yeah.
Yes.
And so what is happening? So let me just explain this diagram. What is happening is written here. So what is happening is that, see, as you drive the quantum system or classical system stronger and stronger, you expect that the region of synchronization should increase because it responds. You're forcing it stronger and stronger. So sorry, I maybe rushed through this argument here. So on this axis, which is basically what is plotted here, is the difference between the drive frequency and the natural frequency. So for a while, the drive frequency, natural.
Okay, yes.
Natural frequency. Yeah. So for a while, basically what is happening is that the drive, the natural frequency locks onto the drive. So that's that flat region here. After which it uncouples and goes back to its drive frequency, basically, to its natural frequency. And that's the reason why you see that. Whereas what happens, so I can ask what happens to this region if I double the forcing amplitude. What happens is it goes from being here to being there. That's what's happening over there.
Okay,
and so that's the reason why when I show you an Arnold tongue like this, for instance, this is the strength of either the interaction, the coupling, or the drive. And so just think of it as a drive strength. So as I'm increasing the drive strength, you're basically seeing a larger and larger region in which basically there is a nice value of synchronization, right? And that's the point here.
Okay, thank you.
Yeah, does that answer?
Yes, thanks.
Yes.
Great. Are there any more questions from the audience? So let's see. Doesn't look like. So I think we should thank our speaker once again. So thank you, Sai.
Thank you very much.
And